Now we're going to pick up our story with Galileo and Newton. We had last talked about Johannes Kepler and Kepler's laws and made the point that although Kepler discovered these laws, he did not offer any kind of explanation for why they were what they are. And so we're going to talk about what happened in the 1600s that allowed finally an explanation for why Kepler's laws are true. So we start with Galileo Galilei, and he helped establish the primacy of experiment and observation in judging an idea's validity. He also disproved a key idea of Aristotle and discovered Newton's first law, and made many discoveries with the newly invented telescope. So the telescope was invented about 1608. Galileo did not invent the telescope. However, he did hear about it, and just based on that description was able to build his own telescopes. And as far as we know, he was really the first person to really look at the sky with the telescope and widely publish his observations, which were done very carefully and explained very, very well in his writings. So here is a drawing of just a myriad stars in the Milky Way. One of Galileo's discoveries was that the Milky Way, which to the naked eye can just appear to be like a liquid swath across the sky, hence the name of Milky Way, upon looking at it with a telescope, a small refracting telescope, really not any better than a pair of binoculars, modern binoculars. He could point at a milky part of the Milky Way, so to speak, and actually see that it was made of many, many stars. And so he showed that the Milky Way is in fact made of many, many stars. He observed the moon and noticed the topography, that is the play of light and shadow highlighting craters and mountains on the moon. This was a big deal because the celestial realm, especially to ecclesiastical authorities and most philosophers at the time, thought that everything in the heavens was perfect. So for the moon to be pockmarked, for it to be uneven, was a shock to many. He observed the moons of Jupiter, specifically the four biggest moons of Jupiter, which we in fact now call the Galilean moons of Jupiter, the four biggest moons of Jupiter. Jupiter has like 60-some moons, but these are the first four that were discovered by Galileo with his telescope. And besides discovering them, it was a big deal because these moons were orbiting around Jupiter. It was obvious upon watching them from over the hours of a single night and from night to night that these moons were orbiting around Jupiter. So that was a big deal because they weren't orbiting around the Earth. And so this provided a evidence that not everything goes around the Earth, and lent, therefore, also some credence to the idea that maybe nothing goes around the Earth other than the moon, and that the planets go around the sun. He also observed the sun itself and noticed sunspots. So sunspots are dark blotches on the surface of the sun. We now know their cause is related to the magnetic fields of the sun, causing areas to be just a little bit cooler than the surrounding areas, and the cooler areas therefore do not radiate as brightly and appear dark in silhouette. But these things are blotchy, they come and go, they're irregular, and again that was a shock because it showed that things in the heavens were not pristine, were not perfect, and these observations were part of what got Galileo in trouble and ultimately convicted and put under house arrest for the last decade or so of his life for contradicting the teachings of the church. So Galileo died in 1642, the same year that Isaac Newton was born. And so what Isaac Newton did is he established fundamental principles explaining motion, gravity, and optics. Along the way, he invented calculus, so you may have had some calculus or at least heard of it. He invented calculus as as a tool, really, when he was trying to figure out how orbits work, and specifically the moon in orbiting the Earth, for instance. And a fun fact about Newton is that in the later years of his life, he really stopped doing science as much as he did when he was younger, and got a job in the British government bureaucracy in charge of the British Mint, and spent a lot of time tracking down and prosecuting counterfeiters. So Newton's laws of motion, you've no doubt heard of those, and here is the traditional phrasing of Newton's laws of motion. N1, Newton's first law: an object at rest will stay at rest, an object in motion will stay in motion with constant speed in a constant direction unless acted upon by a net outside force. Newton's second law: F equals ma, force equals mass times acceleration. Newton's third law: for every action there is an equal and opposite reaction. And these are the traditional phrasings of Newton's laws. I'm going to offer you a slightly different phrasing that I hope contrasts and maybe elaborates a little bit. So for Newton's first law, the way I like to phrase it is that stationary objects naturally stay put. Moving objects naturally coast. So this is a direct refutation of Aristotle. Aristotle believed that all objects naturally come to a stop. And to a casual glance, that seems to make sense. You know, you slide a book across the table, it will come to a stop. But that's because there's friction between the book and the table. If you had a book on a table and there were no friction, like an air hockey table, and you push the book, it will keep going, it will not slow down, it will keep going forever if the table was infinitely long. And in fact, space probes that we send out into space, the Voyager probe, the New Horizon, Voyager probes, I should say, the New Horizons probe, Pioneer probes, you may have heard of. These things are launched from the Earth with big rockets, but once they leave the vicinity of the Earth, there is no rocket engine pushing them. They are just coasting, and they will coast forever. And in fact, these objects are all leaving our solar system, or have left our solar system. So the Newton's second law, acceleration is net force divided by mass. Now, mathematically, F equals ma is equal, means the same thing as A is F over m. So why am I writing it as A is F over m? Is I like to kind of separate it in terms of cause and effect. What causes acceleration is a force, and what resists acceleration is mass, or another word for mass is inertia. So Newton's first law is really a statement of inertia, and mass is how we measure inertia. So F is on top because more force gives you more acceleration. M is on the bottom because more mass gives you less acceleration. It's harder to accelerate an object that's bigger. It's easy to accelerate an object that doesn't have much mass. The other difference in the way that I'm phrasing this, if you've seen F equals ma or heard F equals ma, I put that subscript net, because I want to stress that the F in Newton's second law is really the combination of all the forces acting on an object. Not any one particular force, but if you have more than one force acting, you have to combine those forces to have the resultant or the net or the total force acting on the object. Lastly, Newton's third law: for every action there is an equal and opposite reaction, is the traditional phrasing. I dislike that because people don't really know what the heck the action and the reaction are. So my phrasing is that every force is an interaction between two objects. Each object feels that interaction, but in opposite directions. So for example, let's say you have a car running down the highway and a bug hits the windshield of the car. There's really only one interaction. There's only one contact. The bug and the car are touching each other, and both of them feel the same force. It's a common misconception that the The bug feels the greater force. The bug will certainly feel a greater acceleration or experience a greater acceleration, but it won't experience any more force. And the reason it experiences a greater acceleration is because it has less mass, going back to Newton's second law. But the forces are the same. Any two objects that touch each other, they feel the same touch, just in opposite directions. So when that bug gets hit by the car gets hit by the bug, and the car would slow down a little bit due to that impact. Not much, but a little bit. Besides the laws of motion, Newton also figured out the law of gravity, and he did this when he was trying to figure out why the moon goes around the Earth. And the basic idea behind Newton's law of gravity is that if you have two masses, let's call them m1 and m2, they exert a force on each other that is proportional to their masses. m1 and m2 both factor and are both on top of this fraction. And it's inversely proportional to the distance between them, which we're calling r, that distance squared. So this g here is a constant of proportionality. It's basically just a number. It does have units. The value of the number depends on what units you're using. Here we're using units of newtons, which is the modern SI unit, for a unit of force. Newton is a little less than half of a pound of force. And the numerical value of g will depend on the units. So using newtons for force, meters for distance, and kilograms for mass, g has this value, 6.67 times 10 to the negative 11. And that's a really small number. What g really means in combination with this equation is that if you took 1 kilogram, which is about 2.2 pounds, if you took 1 kilogram and placed it 1 meter away from another kilogram, then the force of gravity between them would be 6.67 times 10 to the negative 11 newtons. Really, really tiny amount of force. And in fact, Newton didn't know the value of big G. He wasn't able to measure it. It was more than a century after Newton figured out the equation for gravity that someone was actually able to measure the value of big G. So that's Newton's law of gravity. And Newton's law of gravity actually allows us to explain Kepler's laws. So again, Kepler's laws were empirical with no explanation why. So it's possible with a couple pages of math to derive all three of Kepler's laws. Now, we're not going to do that here, but in doing that, we see that Kepler's third law actually is a little bit incomplete. So including Newton's law of gravitation, the full equation for Kepler's third law is p squared is equal to a cubed over m1 plus m2, where m1 and m2 are the masses of the two objects that are orbiting. So m1 might be the sun, m2 might be the earth, or maybe m1 is the earth and m2 is the moon or an artificial satellite, whatever it is. Now, this equation does apply, is in the correct form if p is measured in years, the period, and a is measured in astronomical units, just like before. And then the masses have to be measured in solar masses. That is, we're going to use the mass of our sun as a unit of mass rather than kilograms. There is a version of this equation that involves using meters and kilograms and seconds, but we're not going to use that right now. So here's a quick question. If you could magically quadruple the sun's mass, what would happen to the Earth's orbital period? Would it become 4 times longer? Would it become half as long? Would it become 1/4 as long? Or would nothing change? And so if we look at the equation, now we're not going to plug in any actual numbers here, but I just want you to think in terms of proportionalities. So the mass of the sun, let's say m1 is the sun, m2 is the Earth. The Earth's mass is really insignificant compared to the mass of the sun. So if we quadruple the mass of the sun, we basically quadruple the thing in the bottom of the fraction here. So this number, m1 plus m2, is going to become 4 times larger. And so this fraction is going to become 1/4 as much. It's going to be 1/4 as great. And so to find p, we're going to have to take the square root, because this is p squared. And the square root of 1/4 is 1/2. So if we quadrupled the mass of the sun, the Earth would go around the sun twice as fast. It would take half as long. Our year would be 6 months. Now this is a modern version of a famous diagram that Isaac Newton actually drew. It's called Newton's mountain. And the idea here is to imagine that you have a cannon on top of a really tall mountain. And the mountain is so tall that in fact it sticks out above the atmosphere of the Earth. And imagine you fire the cannon. And imagine you fire the cannon really softly, like there's hardly any gunpowder in it at all. Then the cannonball would just kind of pop out of the cannon and fall, right near the base of the mountain. But if you fire the cannon harder and fast enough, the cannonball will curve around the Earth. And if you fire it fast enough, in fact, it will curve around the Earth and not intersect the surface of the Earth. And this is what an orbit is, where the cannonball is feeling the effect of gravity. The cannonball is falling. The cannonball is in free fall. It's just not necessarily getting closer to the ground. So something that is falling but not getting closer to the ground. That sounds a little weird. But gravity is acting on the cannonball. If gravity wasn't acting on the cannonball, then the cannonball would go in a straight line. So the fact that it curves is due to gravity. And if it goes fast enough, it will curve around the Earth. And that's what an orbit is. In the case of the Earth, just above the Earth's atmosphere, the cannonball would have to be fired with a speed of about 8 kilometers per second. That's about 5 miles per second, or 25 times the speed of sound. So that's the basic idea of an orbit. If you fire the cannonball fast enough, that is faster than 8 kilometers per second, the cannonball will go in an elliptical orbit. And if you fire it even faster than about 11 kilometers per second, then the cannonball can escape from the Earth entirely. It can escape. So that's called the escape speed or escape velocity. And something that's going faster than the escape velocity will follow a geometric path that is a hyperbola. If you're shot at exactly the escape velocity, your path will curve in a parabolic shape. You won't come back, but it's kind of the dividing line between a very, very large ellipse and a hyperbola is the parabola. So orbits don't have to be ellipses. If you have just exactly the right speed, you'll be a circle. The orbit will be a circle. If you're going faster than the speed needed for a circular orbit, you'll be in an ellipse. A parabola, if you're going even faster, and even faster than that, a hyperbola. So these geometric shapes, if you had this in geometry class at some point, are called conic sections. If you imagine a cone and you slice the cone, if you slice a cone perpendicular to the axis of the cone, you get a circle. If you slice it at an angle, you get an ellipse. If you slice it at an angle steep enough that it actually matches the angle of the side of the cone, the far side of the cone, you get a parabola. And if you go even steeper than that, it's a hyperbola. So these shapes are called conic sections. A few more vocabulary items here. If you have an orbit of an object going around the sun. The sun is at one focus, as we talked about when we were talking about Kepler. So as a planet goes around the sun, there's going to be a point when it's closest to the sun that's called perihelion, and there's a point where you'll be furthest from the sun that's aphelion. And for the orbit around the Earth, or an orbit around the Earth, say the moon, when it's closest to the Earth, that's called perigee. When it's furthest from the Earth, it's called apogee. And these are coming from Greek. Geos is the Greek word for Earth. Helios is the Greek word for sun. So a question for you. Astronauts in orbit, here are astronauts on the International Space Station. Are they weightless? Now this is a little bit of a trick question because you can answer yes or no depending on your definition of weightless. Now personally, I like the definition of weight that means the pull of gravity. And so in the sense that people in orbit, people in the space station, they're floating around in the space station, but there is the pull of gravity acting on them. If there were no gravity acting on these people and the space station, then they would sail away from the Earth in a straight line. The fact that they're in orbit around the Earth means that there is gravity acting on them. And to my mind, I would call that weight. However, some authors and physicists prefer a different definition of weight, where someone who's floating around in a room, like these folks are considered weightless, because if they try to stand on a scale, the scale will read 0. And that's a fine definition. It's not that it's wrong. It's not that mine is wrong. It's just that there are sort of two different ways of thinking about it. So some people will say these people are weightless. Other people will say they're apparently weightless. And you just have to be careful, whoever you're talking to, what is their sense of the word weightless. A number of years ago, I actually got to fly on an airplane that NASA uses to simulate weightlessness. And it goes by the name of the Weightless Wonder. It's more commonly known as the Vomit Comet, but NASA isn't very fond of that name, actually. And I'm just going to show you a short video clip from the flight that I was on. And the reason this works is that the airplane goes up, it climbs, and then it arcs over. And so the airplane acts basically as a windshield, protecting you. When you jump out of an airplane, you feel weightless for a few seconds as you accelerate towards the ground. But very quickly, air resistance takes over, and you stop accelerating towards the ground. So in the Weightless Wonder, the airplane shields you from any effect of drag, and you are in free fall with no effect of drag. And so it's just like being in orbit in terms of being in free fall. The only difference is that the airplane is not moving to the side fast enough, and in its free fall, it will collide with the ground if they don't pull out. So in the Weightless Wonder on the flights, you only have about 20-25 seconds of weightlessness, or apparent weightlessness, but you do get to float around. We were doing some scientific experiments. There I am, and it is called or nicknamed the Vomit Comet for a reason. A lot of people do get sick. I personally didn't get sick, but I came really close. I wasn't really happy during it, and but anyway, it was a great experience to be on the Weightless Wonder. Now, Kepler's law is talking about planets being following elliptical orbits around the sun. Technically, that's only true if there were only two objects in the universe, the sun and the planet in question. If there are other planets, as of course there are, then their gravity is going to influence other planets. So the Earth, in its orbit around the Sun, does not follow a perfect ellipse because there's the gravity of Venus, there's the gravity of Mars, there's the gravity of Jupiter. And now those forces of gravity from the other planets are constantly changing because the positions of those planets is constantly changing. But they're very, very small. So the Earth's orbit is very close to being an ellipse, but there are small deviations, and a small deviation from that perfect ellipse is called a perturbation. So now we can use this as a tool. In the case of Neptune in the 1840s, Neptune was actually discovered because of perturbations. So Uranus, the planet Uranus, had been discovered in 1781, and basically its discovery was an accident. Two astronomers, William and Caroline Herschel, a brother and sister team in England, discovered Uranus in 1781, just came across it. And over the decades, as astronomers followed the orbit of Uranus, kept track of its position, they noticed that there were subtle differences between where Uranus was and where it was predicted to be, based on the sun's gravity, also based on even taking into account the effect of Saturn's gravity, Jupiter's gravity, that it seemed like that there was the effective gravity of some other object that had not yet been known. And so two mathematicians actually did this calculation. One was French and one was English. The French mathematician, his name was Leverrier. It was Adams, John Adams in England. They both made this calculation more or less at the same time. And Adams wasn't able to get astronomers in England to look, whereas Leverrier was able to get a couple astronomers, Germans actually, to look for this planet whose gravity was affecting Uranus. And the first night, like within an hour or two of searching in the area of the sky that Leverrier had predicted, they discovered the planet Neptune that we now call Neptune. And so that's using gravity, using orbits as a tool for discovering, in this case, a new planet that had never been known before. So a numerical model is is another word for a computer simulation. So I want you to imagine that we have four stars here, these four circles, and their initial positions and velocities are known. And let's look at this orange one. If we use Newton's law of gravity to calculate the gravitational force on the orange star due to the brown, purple, and green star, we can calculate those forces. Now, these forces are all going to be vectors. They have a strength, we say a magnitude, but they also have a direction. And the net force is going to be the vector addition, the vector sum. And in a physics class, you would really get into this and learn how to find the net force from multiple individual forces. We're not going to do that here. But I want you to realize that those three forces are going to combine to have one net effect on the orange star. Now, using Newton's second law, A is equal to F net over m, we have the initial velocity, we have a change in velocity, and we have a new velocity. So acceleration allows us to calculate the change in velocity of the orange star and calculate its new velocity. And then based on the new velocity, we can calculate after an amount of time here, delta t, some time interval. Based on its velocity in the time interval, we can calculate a new position of the orange star. And now imagine doing that for each one of the stars. each star based on the forces felt from the other stars. And then you repeat, and you calculate the position of each star, say, 1 day into the future. And then based on those new positions, 1 day into the future after that, and 1 day into the future, or 1 hour, or 1 decade, whatever the delta t is, you can simulate the motion of stars numerically like this with a computer program. Computers just love doing repetitive calculations like this that would drive a human crazy. But this is how computer simulations work. So this is a still picture from a computer simulation of gravity and orbits. I have the links over here on the left, so hit pause on the video and pop that in there and play with it. I also have a short video here showing the simulation. And so I'm going to let this run a little bit. Here's just a simple planet in an orbit around a star. And one thing I want you to notice with this is, yeah, the planet's going around in a circular orbit, but the sun, the star, also moved. Now here we've got a moon going around a planet as the planet goes around the star. All this is calculated moment by moment. There's no equation that describes these shapes. It's just calculated from 1 second to the next second. Here are 2 planets, one in a very elliptical orbit and one in a nearly circular orbit. Oh, there was a perturbation. That close pass caused that planet to change its shape. I guess really that was a comet, probably, not a planet. Caused it to crash into the sun. That actually happens all the time. Here's a binary star, 2 stars that are orbiting each other, but one of them has a planet around it. Here are 3 objects. Oh, 4 objects. 3 planets, it looks like, in orbit around a star. And here are 4 stars doing a dance. Everything has to be just perfect for this to work. Again, in the numerical simulation, this is just calculated forward 1 moment at a time. Here's another very elliptic orbit, and that was one where there was a close pass of one near the other that caused one planet to be ejected from the solar system. We actually use these gravitational assists, flybys, to send probes. We'll send a probe past Jupiter and it will slingshot it onto Saturn. Here are 3 objects that are going to pass near a star. One followed a parabola, the other 2 are following hyperbolas. And these are elliptic orbits of different eccentricity, different amount that they're stretched out. Now, the previous video was just showing a simulation with, a couple objects, 3 or 4 or 5. You can, with very, very powerful computers, do these simulations with hundreds, thousands, or actually even millions of objects. And so this is an actual computer simulation of 2 galaxies containing, for the purposes of simulation, thousands of stars, not billions, but thousands of stars, and what happens if 2 galaxies collide. So if you want to see that again, go ahead and backtrack on the video and look at it again. And that concludes our discussion of Newton's laws and Newton's law of gravity, and a little bit about Galileo there at the beginning.